Howdy, howdy. This is Mr. Potter. Today we're going to be talking about solving problems involving related rates. In other words, how something changes with respect to how other items that are related change. And so I want to start with a very basic example. So imagine that I'm inflating a balloon. Now, most of the balloons that we deal with are spherical. So we're looking at a formula where the volume is 4/3 pi times the radius cubed. But if I take this equation and I take the derivative with respect to time, then if I take the derivative of v, I'm going to change in volume with respect to time. And if I take the derivative of this side, I end up with 4/3 pi times 3r squared dr dt. And so what I've got is I've got a formula that relates the change in volume over time with the change in the radius over time. And of course, if I'm inflating a balloon, I'm changing its volume, but I'm also changing the radius of the balloon. And so this is really the key premise behind related rates problems. When we're dealing with related rates, the very first thing that we're going to have to do is we're going to have to find a model. So now, I don't know if I'm going to be dealing with geometric models or if I'm dealing with algebraic models. But I know that I've got to be dealing with some type of model, something that relates the quantities that we're talking about. So in the previous example, we were talking about how to relate the change in volume to the change in radius. So I had to come up with some model, some formula that correlated the volume to the radius. So that's the first thing I have to do, is come up with some type of model. And the second thing that I'm going to do is I'm going to take the derivative with respect to time. Now, in the process of taking this derivative with respect to time, anything that depends on time will end up with a derivative that pops out. So volume depended on time. So dVdt came out. The radius depended on time. So drdt came out. But anything that's constant with regards to time, so anything that doesn't relate to time will go to 0. Because if it's not changing over time, it's constant, and we know that the derivative of a constant is 0. And we'll see more examples of how we use that in tomorrow's lesson. But the third thing that I need to do is once I've actually taken this derivative with respect to time, I need to substitute the known quantities. Now, the thing is, whenever I take the derivative, I'm going to end up doubling the number of variables that I had. In the previous problem, my volume equaled 4/3 pi r cubed. I had two variables, volume and radius. When I take the derivative, I end up with not only volume and radius, but dv dt and drdt, because those are variable quantities as well. So I'm going to have to substitute for all of my known quantities. And then, of course, the most important part is to interpret our solution. Because there's a key difference between knowing what a solution is and what an answer is. A solution is just a solution to an equation. It solves an equation. But an answer has to answer a question. And we need to make sure when we're doing these application problems that we're really answering the question involved. Not just finding a number, but actually using that number to answer the question. So I want to go back to the example we were just doing, but I want to talk about it in a little bit more detail. So in this situation, I've got a balloon that's being inflated at 50 cubic inches per second. And I have two questions here. One is how fast is the radius increasing when the radius is 8 inches? And two, how fast is the surface area increasing when that radius is 8 inches? So I'm going back to part 1. I'm dealing with volume changing. So I'm dealing with volume, and I want to know what's happening to the radius. So I need a relationship that involves volume and radius. And we talked about this, of my volume equals 4/3 pi r cubed. That's my first step, coming up with some type of model, in this case a geometric model, that relates volume and radius. And the second thing I need to do is take the derivative with respect to time. So I'm going to be taking the derivative of volume with respect to time. And I'm going to be taking the derivative of my radius with respect to time. Of course, the derivative of this expression, because it's coefficients, I'm going to end up with 4/3 pi times 3r squared, or 4 pi r squared. And that brings up something that's going to be very, very important, and we'll talk about it in just a few moments. But now I've got my change in volume, which I knew to be 50 cubic inches per second. And my radius, which I knew was 8 inches. And now I'm ready to answer the question, how fast is the radius increasing? So 50 equals 4 pi times 8 squared times dr dt. And so I can find that dr dt is equal to 50 over 8 squared is 64 times 4, that's 256 pi. Now this is my solution. And if I put this in my calculator, I'm going to come up with a number like 0.062. But remember that this is the change in radius over time. So the thing is, the radius is increasing at 0.062 inches per second. And here's that important part. The idea is that I had a solution, but I wanted an answer. And there's a difference between these. A solution is just going to be a number, but an answer is actually going to answer the question. How fast is the radius increasing when it's 8 inches? It's increasing at a rate of 0.062 inches per second. So going to the second question here, the second question wants to know how fast is the surface area increasing. So now I need a relationship between surface area and radius. And there's a formula, geometric formula, that the surface area of a sphere is 4 pi r squared. And I mentioned that we would talk about this because this looks very familiar. The thing is, if my volume is changing, where does it change? It can't change at the center of a sphere. It's got to change at the surface of a sphere. That surface is where it's going to change. So my surface area is 4 pi r squared, and I want to take the derivative with respect to t. So I'm talking about the change in surface area over time is equal to 8 pi r times the change in radius over time. And so I've got to use this implicit differentiation that we talked about back in chapter 3. And notice that I have these relationships. I know the radius is 8 inches. I know that we just solved for dr dt in the previous problem. And this is the same balloon, same situation, same circumstances. So I have a formula for the change in surface area over time. It's going to be 8 times pi times 8 times what we came up with over here. And I'm going to use this exact answer, 50 over 256 pi, because it's going to make my calculations a little bit easier. I notice that my pi's will divide out. I notice that 8 times 8 is 64, which leaves me with 4, and I've got 50 divided by 4, which is 12.5. And this is my solution. But remember that this is a change in surface area over time. So the surface area is increasing at 12.5 square inches per second. I have to make sure that I answer the question. Getting the number is not enough. So this is one of the traditional problems that we see in calculus. Another traditional problem deals with the conical tank. So I've got a conical tank that's 10 feet high and 10 feet wide. And I'm filling it with sand at a particular rate, 10 cubic feet per minute. And the question I'm asking here is, how fast is the sand rising when the height is 6 feet? So the first thing I want to do is I want to draw a picture of what we're dealing with. I've got a conical tank, some type of cone, I know that my tank is 10 feet wide and 10 feet high. And my question is, in the situation where I'm filling this up with sand, and when my sand is 6 feet high, how fast is the height rising? So I'm asking how fast is the sand's height rising? This is the change in height over time. So I'm going to need to find some way to relate volume, this 10 cubic feet per minute, which is change in volume over time, with the change in height over time. And I know there's a formula for the volume of a cone. The volume of a cone is 1/3 pi r squared times height. And as we've talked about in section 4.4, having a relation is great, but I really want to be able to take the derivative, and in order to do that, I need a function that relates these two variables. I need a formula for volume that's a function. And I really want it to be volume in terms of height. So that's what I need to come up with. So my question here really is, what is the radius in terms of height? Because if I can figure that out, if I can figure out how the radius and the height are related to each other, then I can replace radius with a function for height. And I can figure out what this formula for volume is in terms of height. So I'm looking at this, and I know that I've got some radius here and some height here. And as I add sand in, it's going to change until ultimately I reach the full container. Now the full container has a height of 10 feet and a radius of 5 feet. But in reality, as I fill this conical tank, I'm going to notice that I have similar triangles. And it's this proportionality of the sides, the fact that the height ratio to the radius is always going to be a 2-to-1 ratio, is what's really going to help me for it. The idea is that my height, whatever my height is divided by my radius, is going to be 2 over 1, because it's that 10 feet to 5 feet ratio. And so my height is always going to be 2 times whatever my radius is. And this is the key. My constraint, if you want to think of that. That allows me to take this relation of volume that involves radius and height and convert it to a function of volume. And in this case, my function of volume is 1/3 pi times h over 2 squared times h. Because if my height is equal to 2 times my r has to be equal to h over 2. And so what I've really got here is that my volume equals 1/12 pi h cubed. So if this is my volume is 1/12 pi h cubed, I need to take the derivative of this with respect to time. And that's going to give me 1/4 pi h squared dh dt. So step 1 is I had to come up with the model, and that was the most time-consuming part here, because I needed to get from a relation to a function. Step 2 is taking the derivative with respect to time, and I'm going to be using implicit differentiation throughout this section. So the derivative of volume gives me dv dt, the derivative of height gives me dh dt. Step 3 is I take the values that I know and I substitute. I know that sand's coming in at 10 cubic feet per minute. That's my change in volume. And I know that my height is 6 feet. So I'm ready to substitute those things in. I've got 10 equals 1/4 pi times 6 squared times dh dt. And I'm ready to solve for dh dt. So I've got 10 equals 9 pi dh dt. And so the change in height over time would be 10 divided by 9 pi. Now remember, this is a solution. So what I need to do now is come up with an actual answer. I need to figure out what 10 divided by 9 pi is. And according to my calculator, that comes out to 0.354. So what I'm talking about here is that the sand is rising at 0.354 feet per minute. So I've got a relationship here as that actually answers the question: how fast is the sand rising? It's rising at about a third of a foot a minute, or about 4 inches per minute. That's how fast the sand is rising in this conical tank. Now, these are just two of the problems that calculus students routinely hit when they're talking about related rates. And these two problems look vastly different, but they have a lot of things in common. This idea first of coming up with some type of relationship, something that brings all of the quantities together. The second thing, this idea of taking the derivative with respect to time, getting everything in terms of a rate of change over time, substituting in our known values. We knew this was 10, we knew this was 6, and we isolate our unknown. And most importantly, the difference between having a solution and having an answer. So, we're going to continue talking about this over the next few days, because these problems really are one of the major applications of the calculus. So this is Mr. Potter. Thank you for watching. Have a great day.